So now for the last talk of this session, for the morning session, we have a game in Onofri, which this time again from Università di Roma 3. And this time we will be speaking about artificial intelligence for traffic data analysis. So the floor is yours.
Thank you very much, and thank you again for the possibility to present my work this time, not literature results. And today I will talk about EA traffic for data analysis, and in particular how the AI can serve models. Actually, this is not work of myself only. I work in a medium-sized group at the National Research Council with Elia and Maya Adriani, who are the organizers of the group, and my co-authors in the paper that will be published in a while, hopefully in a very short time from now on, because we are still finishing last touches. In fact, the last part of this talk has still some open questions. And along with them, I work with Andrea Pella and Caterina Balzotti and Marta Minci. So, our project in this case is called the TPOT project. And TPOT stands for an acronym of Integrated Tracking for Traffic Forecasting and Nowcasting. Not in English, of course, otherwise it would be ITTFN, which makes no sense, but in Italian it's Tracciamento Integrato per la Previsione e l'Osservazione del Traffico. And we did this project with Autovie Venete, which is the owner of the highway structure in Veneto and Friuli-Venezia Giulia. And the idea behind the project was that they have a lot of data, a lot of sensors, a lot of things happen, and they always keep tracking humanly what happens in the grid. While with our project, they sit down, run the simulators, and everything happens like a magic, and so they can take a cup of tea while while working. And actually, this is why TPOT is their line. So, apart from these fun facts, I would like also to make some acknowledgements, because this project was founded with a lot of people founded this project actually. Smart Tour, intelligent platform for tourism, innovative numerical methods for evolutionary partial differential equation and application, and of course also the project by Autovie Venete called Project Sparta and the Project Sparta 2.0. So, which is the problem? We are now to the settings. Again, traffic flow is characterized by two components, parametric in space and time, the density rho and the corresponding physical velocity. And we have seen this yesterday. If you were here, if you were not here, then I will make some small recap, and I think that I have to move closer because it's not working really well. And in real world, this information cannot be measured in each time, in each place and each time of our simulation, but instead we have, of course, some discretization, both in time and space. And of course, the density of the street is really, really hard to measure, because density is something like a physical concept that cannot be actually measured if it is not fluid. We use fluid dynamics rules, but for traffic is not liquid. And so we usually measure flux instead, as the number of cars that pass through some certain point of the street. And this flux, of course, is related with a very trivial rule, which is density multiplied by velocity. So, sensors, as I was saying, are located in fixed points within the streets, and measurement occurs in non-discrete, non-homogeneous, discrete time intervals. So, at some point in time, sensors decide, okay, I give you next data, but we still don't know if there's a fixed amount of time between them. So, real-time analysis, we only know the horizon, of course, up to the horizon of the events, and not to know what will come, otherwise we were not here. And this, of course, is a very crucial problem when it comes to make actual simulations, because you would like to forecast what happens next. So, task we faced in this project is to analyze traffic flow, and analyze traffic flow means reconstruct flux and velocity up to time, up to the horizon of the events. Because of course we said that the grid, the points of measurement are scattered around the street, and of course also to predict the traffic flows, which implies of course understanding what will come next. Knowing the data for a sparse set of points is not enough to answer even simpler questions like, okay, I give you this sensor, I give you this data, I would like to know what happened now or maybe in 5 minutes, 1 kilometer after, 1 kilometer before. And it is very simple to understand because we can make some examples. A few vehicles are detected with a limited speed with respect to the speed limits. What's happening? Is it because there's traffic, or is it because probably maybe the weather is not good, so they are slowing down, but there's no traffic at all, or other stuff like that, or maybe a crash happens a few meters before the sensor, so we don't see any car passing, or maybe only a few vehicles passing, and we still don't know that a car crash happens a few meters before. And typically no car are detected for a few minutes, then my sensor says, okay, velocity is none, because we don't know anything about what's happening. No cars were detected, but where's the point here? You should say, okay, my density of the street is like 0. But then it is not true, because maybe there is a very, very, very bad jam happening, so the cars are still under the sensor is not able to detect the car that is not moving, so I reconstruct in my model that the street is completely empty, and instead it is completely full, and a mess happens, because of course these models are thought in order to make the owner of the street take a very careful decision, like closing some gates, or maybe send some emergency vehicles or stuff like that. And of course, this decision costs money, and of course, they don't want to waste money. So timing in detection of potentially dangerous situation is very crucial, and so we would like to refine as possible our measurements and our simulation. Here we have a very simple sample of measurement data. This is a sensor that is measuring velocity, speed, and flux during an entire day. And you see this very, very high variation in flux. In the velocity is something like constants about 90 kilometers per hour. This is from the lane of the heavy vehicles, so they are not reaching 130 kilometers per hour or stuff like that. But still, we cannot understand many things from this, because of course there are points scattered, and then I told you that if it is like 6 a.m., then we don't know what will come next, so we cannot make accurate prediction. First thing we can do is, for example, to refine them with some normalization in the flux that is typically very useful when it comes to modeling. It's made with Gaussian filtering, very simply by applying triangular kernelization to some sides, in this case 10, and so these are the data. Very problematic real example is for this one. Let us consider that we know up to this point in the horizon time of the events, and we see that here the velocity is start decreasing, so we put on the alarm because something very weird is happening, but instead then nothing happens and everything keeps back to the normality without any further problem. At the same, on the same situation, but on the opposite side, we have here another moment in time. We only know up to this point, which is our horizon time of the event, and suddenly something happens. And the question is, can we predict these two situations? Can we distinct these two situations by knowing up to the time of the event? Well, actually, in this case, yes, because there's some irregularity in the flux. We don't see any very big oscillation in it, apart from maybe here that something like this decreasing. But at the end of the day, if a human being would see this plot, then he will state probably nothing like that. Here it is something like more complicated, but there's a hint, an hidden hint, which is the velocity is 50 kilometers per hour, so something weird is already happening. But and so a human being could say, okay, probably in a very small amount of time something will happen. So, well, where's the point of the rest of my talk? I will discuss about the dataset, so giving some hints about what this sensor do, what the sensor cannot do, and stuff like that. I will present the supervised enriching tool that we have developed. It is very simple indeed, but is very effective in this situation. And we will see how this supervised enriching tool can be useful for computation of the expected traffic volume and for congestion detection and forecasting. Then we will give a brief recap on the microscopic traffic models. So if all of you were here yesterday, I will skip that part, but since we are also recording, maybe I will just give you a few remarks. And finally, we will see how this data, in particular this enrichment, can be fed into the traffic models and then obtain better results. So, the dataset. Any question? Okay, perfect. The dataset. The benchmark dataset, as I was saying, is provided by Autovie Venete. The data come from the 4 highways in Veneto and Friuli-Venezia Giulia. I don't expect you to know where actually this point is, but we have a very interesting map that resembles us. Here there's Trieste and here there's Venice. So we analyzed this part of the highway grid. And of course the main arterial road is the A4, which is a very long highway in Italy. We only analyze, of course, this portion depicted here. The other 3 highways are smaller, and in fact they have only 2 lanes per carriage, while A4 mostly have 3 lanes per carriage. So we already know that something will change between the data of these 3, the first 3 and the last 4th highway. Okay, they've set. Okay. The benchmark dataset was collected between September 2020 and March 2022, and in particular, yeah, but yesterday I was here and what happened, so I was continuing writing. So, okay, then I gathered by 45 ensembles of sensors scattered during these highways. An ensemble of sensors means that per each lane we have a sensor that is measuring the flux, and the ensemble, because if there are 2 lanes, then there are 2 sensors. If there are 3 lanes, then there are 3 sensors. And these sensors are scattered about 1 to 20 kilometers in some point that they know that there's many problems, then they will have a refined grid in some sense. If we talk about numerical analysis, and in other place they have very sparse amount of sensor, and of course this is very important also for our modeling point of view, because if they don't have sensor, then maybe they would like to know what is happening in the middle of 2 sensors, and for this reason we tried also to develop some kind of virtual sensors that mimic the real one based on the simulation output. Ensemble records individual vehicles that cross given spot, as I was saying, and also it classifies the kind of vehicle. I am not from Germany, so, and hopefully no one of you is from Germany, because otherwise I will completely misspell it. The technische for the TLS method, so that classifies between 5 different kind of vehicles plus 1 kind which is the outliers classification. Of course, we use this classification also in our modeling approach. If you remember yesterday, I talked about coupling the models between different kind of vehicles, and we did it with two different kind of labels, namely the light one and the heavy one. So we actually aggregated the class here, the classes here presented, and hey, there's nothing more. So real time versus offline work is a very important point here, because we can access in real time an evanescent time window of 2 hours. Then the data are no longer available. So in real-time prediction, our time window of analysis is only 2 hours. Of course, so the sensor record the data, they give us to make analysis, and then they burn it. No, I'm joking, of course. They also historicize this data in a different dataset and different database, but it is reasonably exploitable, but not in real time actually. And of course, they also have historicized data from the very past year, like I think since 2014 or something. So a very big amount of databases to work on. And I have to point out that this is a very important point, because if you ever been to a traffic conference, then they make like, okay, we have used this beautiful data set of 2 days of measurement, and then you say, okay, can you do 2 days of measurement? Or maybe, oh yes, we have this sensor, they transmit 1 data per hour. Perfect, again, but you cannot exploit them really. So this data set was very, very important and really useful for our research. So, in particular, 17 of the 106 sensors deployed are equipped with advanced technologies. What do I mean with advanced technologies? That actually they are able to define if a vehicle is standing still beneath the sensor. It's a very stupid thing actually, but from a technological point of view, it is not so simple, because they have to combine Doppler radar, the ultrasound emitters, the passive infrared radiation detector, other stuff. I'm not an engineering, so I really do not know actually how they work, but in some sense they are able to determine the congestion condition. The additional information is stored as a Boolean flag, but it is not available at the time, at the present time. And this is also very important. And one of the work was, in fact, to make all the sensors able to detect between these two conditions. So we will use we will use this data as our ground truth. So we call this sensor 3T only because it used 3 technologies. So it seems like it fit the name. And it is from the manufacturer. Is a picture from the manufacturer. Okay. So, supervised enriching tool. Why supervised enriching tool? Why do we not use like clustering or stuff like that, where we do not have to have ground data? Because of course they are simple to use, they are simpler to tune, and they are more reliable. So our main task was to forecast the expected average flux via the historical data available and the detection of congestion events. And human beings are able to do so. We have seen some plots. We have seen that at the end of the day, a human that looks at data is able to do so. So what's better than using a neural network or stuff like that, machine learning tools? They were developed in this way for this reason. If you do remember, probably, I don't know if all of you knows about machine learning neural networks, because we talked on the other room, but they were born like emulating the real dendrons in the brain, making stuff and so these kind of things. So we decided to use them also in this situation. And in particular, between neural networks, so we focus on supervised approaches, we said, and recurrent neural networks proved to be very effective in time series analysis, since we have data that have a very prominent time point of view. I mean that, of course, they cannot be reassembled in other ways. Then we use the recurrent neural network. In particular, of course, probably all of you knows about the LSTM, which are the long short-term memory, which are capable to understand and capture feature or dependencies in long range of times. So, what does this very beautiful phrase means that I have copied from some textbook? It means that actually using an LSTM admits us to have a compressed representation of the data in some sense, and this compressed representation still stores some information, the most valuable information from the LSTM point of view, of the data that were passed 2 hours ago instead of the data that were passed 1 minute ago. So, simple, very, very short introduction to LSTM if any one of you does not know what they are. They are, of course, a neural network, so they have the classical form of some computing units that receive input and gives an output. The very interesting part of LSTM is that the output is kept separated from the pre-processed data. So we have two different sets of information inside the LSTM, which are the output itself, h of t, and the internal memory ct, which is also called cell size. It is called also the h of t is called hidden layer, so hidden information or hidden state. This is why we call it h. So the cell state is updated on the normalized, eventually, novel input that we pass each and every minute, and the size of the cell state and of the hidden state are the actual memory, the actual time window that the LSTM is able to, in some sense, store in its brain. And this will be important in a second. Only a few notation that are not very, very important for the talk, but only for the global understanding of what we are talking about. LSTM works on 4 gates. These gates have a very fancy way to be defined with the hyperbolic tangent or sigmoid. And why there are 4 gates? Because each gate is something like a linear combination of the data, which has different objectives, namely giving the new input and making the decision of what to keep and what to forget at the next step of time and stuff like that. I will just shorten myself up. So this is the LSTM structure. I have to create the figure because I didn't have time to prepare one for myself, and I still need it also for the paper. So maybe in the last version of the slide I will give you, there will be another image. And so this is the output of the neural network, of the LSTM, and we have these 4 states. Okay. Hopefully it was not so annoying. The complete model, which is at this point, the output of the LSTM is a vector, is not a single feature, so we have to take this output and we have to process it in some way. We use the vanilla MLP in order to do so, and okay, sorry, that's the point. We use the vanilla MLP in order to do so, and thank you. Seems to work better.
Okay, then you tell me the order.
I drop it. No, but if I am still here and I use it on my back, on the back of my backbone, then it will work. So we choose a vanilla multi-layer perceptron as this tool. In reality, we cannot say it is a really multi-layer perceptron because only have one single layer, but still it is in this kind of definition. Then we have 2 different tasks, a prediction task, where we would like to predict, in our case, the flux of the upcoming minutes, and a classification task, where we would like to use some very, very fancy technique, like namely converting these values into probabilities in order to detect if there is a queue or there is not a queue, or more in general, a congestion event. And we recall the softmax because maybe someone of you don't remember it, but it's simple normalization of other weights. And so, in a very simple way to explain it, we have the sensor data. We plug this sensor data into a normalizer. So we would like to extract only the normalized version because neural network usually works better in this situation. We apply the LSTM, which has some feedback and makes its magic and stuff like that. and then we plug the result into a multi-layered perceptron. And if we are trying to perform a prediction task, then we simply predict the value, which is actually the output itself of the MLP. If instead we want a classification task, then we use the softmax to so convert into classes probabilities this value, and we output the classification itself. So I think that is very clear, but if any one of you has any question about it, let's ask. Okay, computational of the expected traffic volume. So the first of the two tasks, and how many time do I still have? It was 50 minutes, yes?
20 minutes.
That's perfect. Computation of the expected traffic volume was the first task. So we have a prediction task, and we want, of course, to find an objective function. The objective function in our case is simply the upcoming flux divided by the mean upcoming flux. And of course, it is very simple to obtain ground truth, because offline we have the real data that will come next, so we can compute each and every minute. And since we have such a large amount of ground truth, then we are going to tackle the problem class-wise instead of sensor-wise, meaning that we will give an output for the flux of the light vehicles and the flux of heavy vehicles. And in particular, we can work sensor by sensor, since actually we have so much data that we can tune them sensor by sensor without any loss in accuracy or something like that. And of course, it will work better because different sensors usually have different slope of the traffic. So we can refine our definition here of the target function in a very fancy way, where we are entangling in some sense the two flux of heavy and light vehicles. This is, of course, does not modify our way to evaluate the ground truth, but gives us in mind that the multi-layered perceptron and the STM could, in some sense, make these two flux interact in order to give a better prediction. So we used the data available from 2021, the entire year, and due to the high number, I said that we tune a predictor per emplacement. We organized the two flux in day-length sequences. So actually, day-length sequences means 1,440 data. Sorry, because we gave. I think I forgot to say that these data are transmitted minute by minute. Actually, so these are the number of minutes inside the day. And then what can we say? 1 month of the sample were used as test set in order to validate our results, and we focused in this presentation on only 4 emplacements, which are the boundary of the net, since of course then we will use it in the model to predict the boundary condition. So this is again our model I've reported. We choose a time window of 30 minutes, because usually in our model we predict up to 30 minutes after. Data requires of course, an input of 2 elements, the 2 fluxes. The prediction has 2 elements, the flux of the 2 classes, and NH is a free parameter. So, since we are also scientists and not only people who randomly pick numbers, we try to tune the better parameter as possible. I would like to say that we use a Latin hypercube solution, but of course this is only a parameter, so we just tried every one of them, and we tune it with so these are details of very little interest for us. We choose the root mean square error, and these are the results. These are the results. I'm not showing you these results because we are interested itself in the learning tool, but because there is a very, very interesting point. We would like to expect that the more data we give to the model, the best the accuracy would be. Instead, it is not. Since we are trying to predict the upcoming flux for the next 30 minutes, it seems to be that a time window of around 30 minutes is sufficient in order to get the best prediction. Why this is true? Because of course traffic has no memory. only the time of the day, in some sense, can influence the going of the traffic. So only relying on the last 30 minutes is better than relying on a time window of another 20 minutes, and this is probably because we are putting a lot of noise, adding more data that are not really needed. And another very important thing is that why we don't want to train a single model for all the emplacements, and why do we train a different model for all the emplacements. This is a beautiful matrix where on the diagonal we have an emplacement network used to predict the emplacement values, while off diagonal we have the corresponding emplacement predicted with the other emplacement tuning. So what actually this means is that if we use, and I'm sorry, some of the pictures are still in Italian, really sorry, but it was because we're still writing the paper. And so if we use, for example, the network from Pomigliano exit, then if we use to approximate the data from Trieste exit, then the expected difference between reality is much more better. From 18 mean of 18 vehicles per hour loss, we obtain 37 or 36. And this is only to say that tuning different models is in some sense important, since we want a very high accuracy, or better, as high as possible. And this is a very simple example of what the net does in a very pictorial way. So we have the flux up to the time horizon, and then we don't know what's happened next. The blue line is the LSTM prediction, the model prediction in some sense. The yellow dotted line is the correct prediction, so the real average of the flux, while the red line is something only a mean of the last minutes, just to give an overview of what's the point. Because earlier in the model they used the mean of the previous 10 minutes in order to predict, so it's something like boundary condition, static boundary condition. Okay, congestion detection and forecasting is the other. I don't know what. Okay, sorry, I pushed the wrong button. Okay, the other task was to, I was saying, detect and forecast congestion. I think that I have to speed up a little bit. And so we use, of course, our 3 technology sensor in order to provide the ground truth. But where's the point? The point is that alarm are given sensor-wise, so we have to aggregate the classes. We can no longer distinguish between light and heavy vehicles, and this also makes sense because, of course, if heavy vehicles are stuck in a lane, then you cannot have the cars passing beneath them. Go ahead. And so we did the data set, which is very similar as before. We found out that congestions very hopefully are very low. The number of congestion is very low during the day, so we selected only the days where there were at least some interesting situation. And then instead of performing data augmentation, which means copying the data that are interesting, we preferred to tune the loss function, which is the way the model decides how to update itself in order to weighten the classes. So, what's the problem here? We do not have, actually, a definition of congestion. So we are making something without understanding what we are making actually. And we are mathematicians, we don't like it. So we tried to figure it out a way to define congestion more or less formally. So also, we did not only take the data from the sensor themselves, also because the manufacturer didn't tell us why specific data was classified like a congestion and why another data was not. And we tried to design some heuristics in order to figure it out, what a congestion is and what a congestion is not. And we did it on two levels. We did it on the first level working on flux, and we perform some evaluation about, of course, the regularized data, because they are much more interesting, as we said at the beginning of the talk. And we did this simple heuristic, which means that the actual flux must be low, and the regularized flux must be low, and the mean of the flux must be of interest quite high. Why? Because of course, if I have very low fluxes, but they are still low for the entire day, probably this is not a congestion. It is only that maybe the road is closed or stuff like that. And we did the same thing also for the speed in a very similar fashion, requiring that the speed is indeed below 65 kilometers, because otherwise it not makes sense to talk about congestions, but of course that the average velocity of the time window is higher than 40 kilometers because of the same reason as before. So they both use data that are not available at the time, because they use this regularized version that also looks on the future, and because otherwise we did not a machine learning tool if we had heuristics. And so it is slightly impossible to train one model per sensor in this situation, because the three technology sensors are only a few of the complete fleet of sensors. So we opted for a different way of building the model. We analyzed the mean and standard deviation. We found out that the sensor displaced on the A4, which was the main arterial road, were very different from the other, and so we trained two different ways. I will skip the details because they are not very interesting. We use this loss function, which was weighted not on the classes, and this is what we obtained. We obtained that a time window of 2 hours was the best of the parameters. Why this is important? Because probably if we add more data in this case, despite the other one, we would obtain better results. And just to give you some hints on what's happening, these are days. These are the black one is of course the regularized flux, and this is how our machine learning technique is behaving. I know that you are not here in order to see machine learning stuff, so now we go to the part of numerical analysis, which is instead very not finished yet. So we have still many open problems. Before going to that, I just mentioned that we also made some forecasting, as I was saying. So in order to understand if from the data available at the moment we are able to detect a future congestion, which is very interesting in its own, despite apart from the model point of view. And so we performed something very similar as before, where we tried each and every time window in order to understand what to do. And this is what we obtained. Of course, here we know that the closer is the point in time, the better will be our prediction. And I will skip these results because, of course, we have no time. And well, a step further, we implemented also a very large framework that they are really using in real life right now while we are talking, which is a very surprising fact for a numerical analyst. I think that is the first time project that we made with the National Research Council about traffic was really deployed in action, and it is really used in order to take decision. And we developed this tool in order to predict these queue events and to detect other points. And it's interesting because these red crosses are the minute at which the queue happens, the jam happens, and we are really able to predict up to 5 minutes before what's going on, and even with the smaller probability, even to predict any further. Okay, so very briefly, were you all here yesterday? Because in that case I will skip it, this part. Lighting Whittingham Richard model, LWR. We do recover that it is based on the fluid dynamics idea, and the entirety of the work works on the definition of the velocity with respect to the flux and to the density. And this implies that the function of the flux is this one, and I will move closer. And then we can recover the fundamental diagram, which will be very important in just a few minutes. And of course, we also recovered, yesterday we said that the characteristics cannot be as faster than the cars, because otherwise it's something like cars are influenced from what's happening behind them. But in this moment, we are also interested in how characteristic moves, because of course, when we are modeling the actual solution of the problem, we have to understand what to do in the upcoming space and in the forthcoming space, because I do remember you that the model works on a barycentric grid, but we only have data at sensor, which represents an nodal grid of our discretization in space. So, Riemann problem, I will skip it because you already know the solution. So we know that we can have rarefaction and shock curves, and the solution of rarefaction is a rarefaction fan, while the solution of the Riemann of the shock is a shock curve that for some reason should have been here. And the Godunov scheme idea is that we can use this part of theory in order to obtain a real solution of the model. And here is the really important part, because as I was saying, we have the sensor data, which are in some sense this point of the grid. Then we will of course refine the grid for a very simple reason that we want to understand what's happening inside the street and not only at the sensors. But anyway, the main grid node of the grid will be the sensors themselves. And so we can feed the traffic model with the enriched data. So the two main tasks that we will talk are flux versus density, in the sense that how can we help the model to detect the rest of the street, what's happening in the rest of the street apart from the nodes. Well, we know that we can, of course, use the model itself, the Godunov scheme, in order to, while having the data from the 2 hours before, we can in some sense predict what's happening between the two sensors, two given sensors. But the point is that we do not know the flux, we do know the flux of the sensor, and in some sense it's everything we need, because Godunov scheme requires flux-like interfaces. If you remember, the Godunov scheme uses the density in order to retrieve the flux, in order to preserve the mass. But the point is that the real data are not typically reliable. What does I mean? That you impose that from the right part of the scheme they are exiting, don't know, 10 cars. Then you have 3 cars in your street, and then you end up with minus 7 cars in your street. Very typical situation. And this is a problem because, of course, if you do not resolve the problem, this thing, everything blow up. And so the first solution is that we cannot use these data as they are, because of course they will cause unfeasible evolution of the problem. The first way we can tackle this is to project the flux on the admissible flux set, which is a very interesting solution, because we take the flux that is given by the sensor, the model gives us, okay, look, the flux can only be in this fixed range. Then we project the point of this space which is closer to the flux that the sensor is giving to me. But what's the point here? The point is that it's really worthy to do so, and in particular that the flux itself from the sensor, maybe in one moment is 3 vehicles, next moment is 7 vehicles, next moment again is 0 vehicles, and so on. So there is no regularity in the flux itself, and so you obtain something that is not very stable from the modelist point of view. Therefore, we have a fantastic fundamental diagram. We have flux. The idea is that we put our flux inside the y-axis, and we try to recover where inside here we are. Of course, this is not bijective, so there will be not a single solution. But idea of the ideas, we use the machine learning tool in order to determine on which side of our fundamental diagram we are. What does this mean? This means that we can derive density with a high probability using the probability given by the model we described earlier, And this gives us good results. They are not the best results of the world, I have to admit, we are still working on it, but the error that is committed is different, and it is in different situations. Let's take a very simple example. Suppose that this is the space on the x, the density on the y, and it is something like an instant shot in time. And so, what do we have? That our sensor says that more or less, if we simply invert the function without any further tool, we get that the density is very low for the entirety of the street. At some point, the sensor probably is here, and it drops. Because maybe somewhere around the sensor there was a crash, and then the street is nearly completely empty. It is not completely empty. We have some oscillation here. We cannot see because probably it was better to put in a log scale, but and what's the point? The point is that perfect. You have a clean point. You have the street is completely empty. You run Godunov model, and what do you obtain? You obtain that here characteristics are at the maximum slope, and therefore everything keeps going even faster than if the density was constant. So the idea is that if we detect some kind of Q at the sensor, we impose hardly that the density must be at maximum, which is around 110 for this kind of street. We evaluated with physical in a physical way, and we impose it to be the maximum, so that here the characteristic imposes that no more car can pass. And what we will obtain is that this Q in the future will move slightly backwards, while this street will remain empty afterwards. And of course, this is not the solution of the world, and we have still to work about it, but it works. Last but not least, helping in the forecaster. So now we are trying to determine what will come next, but of course, all of you is numerical analyst. You know that if you plug your models into the world, you need to know what happens at the boundary of your space. So we of course have the idea. Getting back to yesterday's plot, we have here our u0 of x, the initial condition of the street. But if we are limiting ourselves in an interval from alpha to beta, this is the time, this is the space. In order to propagate the solution at each and every time after, of course you need to know what's happened here, because it's of course very important. Perfect. So we need to use the other method we introduced earlier in order to obtain something interesting here. So each and every numerical, okay, this is what I said. We need to estimate the accuracy and predict to reality. So we use our method, and the higher is the time needed, the more difficult it is to predict. So we use the data, and we obtain a very, very beautiful plot that I cannot show you now because it is not ready. But anyway, I'm really sorry about it. We are still working on it. In a few weeks, the paper will be published on Archive and later submitted to some journal. And so, thank you for your attention. Hope you enjoyed the presentation. I'm here for answers.